So we will start with Jonathan Mochel. He's working between France, the Pyrenees, and United States. And he's going to explain in easy words his amazing job.
All right, good morning. Very glad to be here with you. Thank you so much, Vicky and everybody for the nice invitation to speak today. So I know that you all came to listen to Luca, so I tried to make it as short as possible. We've all been to those, conference or concerts where you have to listen to someone before the main event kicks in. So I'm that guy, basically. I try to keep it as interesting as I can. While I have to be honest with you guys, talking about mathematics and pharmacology at 9 in the morning on a weekend after a night of drinking, not the easiest task on earth, but I try to make it work. So my main job for today is to show you how mathematics and clinical science can work together to produce a tool that can be used for dose optimization and PMed applications in veterinary medicine. And so what we're going to do, literally, is try to break through the black box that stands between what we think is an optimal dose of a drug, in that case an ACE inhibitor, and its optimal therapeutic response. And we know it's a matter of debate, right? I mean, some of the practitioners, especially in the US, will use a high dose of 0.5 mg per kg twice a day, while mainly in Europe we'll be using a dose of 0.25 mg per kg once a day. So there's kind of a fourfold difference in the range of those doses. So it's obviously something that we need to investigate. And to do this, we need to actually revisit two paradigms. The first is the way we characterize the biology of the renin-angiotensin system. And the second is the analytical tool we use to quantify the effect of therapeutic drugs on those biomarkers. And we will start with the biology of the RAS first. So what we used to know about the renin-angiotensin pathway, mainly revolving around the angiotensin 2 aldosterone axis, is really just the tip of the iceberg. Practically at least 3 new axes have been discovered in the kidneys and other tissues, and they include the prorenin MAP kinase pathway, the ACE4 angiotensin T4 cascade, and of course the ACE2 pathway that leads to the upregulation of Ang17 and Ang19 that we know have opposite effect to Ang2 and aldosterone. So they have positive effect overall with anti-fibrosis effect, anti-hypertrophic effect, vasodilation, and anti-oxidation. So what you actually want to do is you want to activate that system to lead to therapeutic benefit. And so any attempt to characterize the effect of a drug on the RAS should be done in combination with its effect on the classical pathway, the angiotensin 2 aldosterone pathway, and the alternative pathway, which is the ACE2, Ang17, and Ang19 pathway. Something which I like to use the analogy for the dark force versus the light side of the force, basically. Unfortunately, most studies on the effect of ACE inhibitors in VetMed have been using something called ACE activity as a marker of clinical activity. And those studies have shown in the early 90s that doses above 0.25 mg per kg once a day did not produce any added benefit on the RAS. And they were used to support the initial dose selection of 0.25 mg per kg once a day in dogs with congestive heart failure. Well, practically, we know now that ACE activity is not a reliable marker of RAS modulation. And many studies, especially on the human side, have shown that you can have a complete inhibition of ACE activity, but very high level of angiotensin 2, which is ACE product, as you know. And so there is not a good correlation between ACE inhibition per se and the actual end product angiotensin II in those patients. And as opposed to ACE activity, Ang2 and aldosterone have been shown to be significant predictors of morbidity and mortality in congestive heart failure. So if you want to really characterize the effect of an ACE inhibitor, you have to dig into their effect into those angiotensins and aldosterone to be able to get a comprehensive picture. Now, what I find to be very interesting is that the information we get from the real-world use of those drugs from the clinics, from you guys, is that in practice, specialists recommend the use of ACE inhibitors at 0.5 mg per kg twice a day. So they actually recommend to use a dose which is larger than the one that was initially based on ACE activity alone as a marker of clinical activity. And therefore, it's kind of a way to get from the ground, from the clinic, information to validate the fact that maybe that initial dose of 0.25 mg per kg once a day was not the optimal one to start with. Now, very interestingly as well, any effect, any attempt to characterize the effect of an ACE inhibitors on those patients must take into account the underlying chronobiology of the renin-angiotensin systems. And studies have shown in humans that the time of drug administration had a significant effect on the therapeutic efficacy of those drugs. And this was confirmed in a study of more than 20,000 patients recently that showed that the risk of cardiovascular disease in patients receiving their drugs at bedtime was on average 40% lower than those patients receiving the same drugs in the morning. For hypertensive patients, if they take an ACE inhibitors just before bedtime, they get about 30% increased efficacy in blood pressure monitoring and management versus those who take the same drugs in the morning. So the underlying chronobiology of the system is important to factor in to also maximize the effect of therapeutic drugs. What we did see and show in dogs is that those biomarkers also oscillate with an underlying chronobiology, and that in particular, the time of food administration was the kicker, was the driver of those oscillations. So what you may want to do is optimizing the time of dose administration, the time of food administration, to get the maximum efficacy on those therapeutic drugs. For instance, you may want to dose these dogs at a time where the RAS is at its maximum activity, right? Because then you have the maximum effect of modulating the RAS when its activity is at its peak, basically. So now that we have characterized a bit more the biology of the RAS, I would like to spend a few more minutes on the tools we are using to quantify the effect of those drugs in the first place. And these, as you know, rely heavily on statistics, right? And we've all been writing grants or reading papers or writing papers, and we all have been basically bombed by reviewers' comments about what about your statistics, what about your power analysis, and so forth. My opinion on this is that it's all BS, right? In practice, stats have been designed for the analysis of very homogeneous population, right? So if you work with mice, which are like gene edited, they are very similar. You can play with 9 to 10 mice, that's okay. If you work now with human clinical trials, yes, you have lots of variability in the background, but you have thousands of patients to make it up for that background noise with having actually a better signal in the first place. What we're typically dealing with in animal health is studies of like 10 to 50 animals with a huge background variability. So we have huge variations because of breeds, because of species, because of gender and so forth, and we can't afford to run studies with thousands of patients. So small sample size and very heterogeneous population. And we kind of take that sample size to make inferences, extrapolations on the entire population of dogs and cats. We have a sample of 10 dogs, right, which can be, I don't know, beagles with blue eyes, small tail, and we say, yep, what I've seen those beagles translate to the whole population of dogs on Earth. This is a major scientific flaw, right? It's a very large violation of the basic assumptions in statistics. So stats, in my opinion, is not the right way of approaching data we generate in animal health. And as opposed to statistics, something like computational models, mathematics, actually take into account a large pool of data to make small extrapolation on very specific subset of populations, right? So it's kind of an inverse problem in that case. And if you use mathematics, you may be able to solve mechanistic questions in animal health. And that's maybe the best way to summarize what I've been trying to say over the last 5 minutes. The difference between stats and math, you can say anything you want with your data if you find the right test. We've all been playing with different statistical tests to get to a p-value of 0.05. We've all been there. This is not the way science should be designed in the first place. All right? Good. So now, I'd like to move to our case study. And this case study was practically done to fill that knowledge gap. We tried to leverage the value of comprehensive fingerprinting on the RAS and mathematical modeling to really try to break through that question about what is the optimal dose of an ACE inhibitor. And so the objective of that study were twofold. First, we wanted to characterize the exposure response of ACE inhibitors, benazepril in that case, on biomarkers which we know are relevant to the pathology of congestive heart failure. So not ACE activity, but angiotensins and aldosterone. Second, we wanted to build a tool that can be used by practitioners, anybody on a phone or an app, to basically be able to simulate different doses of an ACE inhibitor and see what could be the optimum dose to be using to modulate the renin-angiotensin system. So very briefly, the study was composed of 3 groups of 3 dogs. We had 9 dogs in a partial crossover design. I only have 2 groups presented here just to make it easier to understand. And what we did is that we randomized those dogs into 3 dosing groups. One was 0.125 mg per kg twice a day. Then we had 0.25 mg per kg twice a day, and then 0.5 mg per kg once a day. And we used a model, which is the low sodium diet model, to activate the RAS to mimic what we actually see in dogs with congestive heart failure. The dogs were actually dosed for just 1 day, and we had a 10-day washout period between studies, and then we collected for 24 hours blood to characterize the PK, so the benazepril concentration in those dogs, and all of the concentration of the angiotensins. And I won't be going into too much details here because it's extremely technical, but the bottom line is that when you build a mathematical model, you're trying to characterize the biology of the system plus the effect of the therapeutic drugs. So you're playing with equations to say, okay, I know that the effect of benazepril on the RAS is this. I'm going to use mathematics to characterize those relationships, and then I'm going to say, okay, now if I change my input dose of benazepril, what is the expected effect I see on those biomarkers? You know that benazepril is going to inhibit angiotensin 2, for instance. You know it's going to also activate the angiotensin 1-7 pathway as well. So once you have that knowledge figured out, you can just use mathematics to say, this is my model, and when I change my input function, my dose, I can now see the effect of that change in input on the output, which is those biomarkers. So these slides is kind of summarizing the predictive performances of that model. So what you actually see here, for each biomarker, you have on the y-axis the observed data, and on the x-axis you have the predicted information from the mathematical model. What you want to see is that those points are aligned on the line of identity, which means that the predictions equal the observation. And you can see that here, most of our predictions were extremely aligned with the observed data. So we know that that model is able to characterize very reliably the experimental data for all biomarkers of interest. Another way to look at this validation is to now look at the individual data for each dog. So in that plot, you actually see circles, which are the experimental data, and a continuous line, which is the model-based prediction. Again, what you want to see is that the model is able to reproduce your experimental data. And that's what we actually have for most of those biomarkers and most of those dogs. So we know we have a model which is able to capture the PK and the efficacy of benazepril on all the angiotensins in those dogs. And once you reach that goal, the next step is the exciting one. Because once you have a model which is functioning, you can use that model to simulate things you have not observed experimentally. You can simulate what we call what-if scenarios, right? You can say, okay, I know I can do a good job in characterizing my PK and PD for those 3 doses, which I have tested. Now I can simulate the effect for a dose I have never tested in the first place. And that's why it's extremely powerful, and it's heavily used on the human side because those big pharmas are going to be able to simulate tons of clinical trials and tons of patients to identify the optimal dose to be tested in development phases to get the maximal efficacy. So now if you click on that link, or if you just scan that barcode, you'd get 20% discount on all Seva products. Just kidding, it's actually 30%. But you actually get access to the simulator which we built online. So we're gonna do this, and I won't be doing a demo just now because we will do that during the roundtable, but just to give you a feel for what the tool looks like, I'm gonna show it to you. So that is a tool which actually you can access, on your phone, on your laptop, anything. And then if you go to dosage comparison here, you have a tab with multiple options. You can compare up to 4 dosing regimen right now. So what you do is that you select the number of doses you want to compare. Let's say we're going to compare 3 doses. And the first dose will be the typical 0.25 mg per kg once a day that we typically use in Europe. We're going to do this for 2 weeks, so 14 doses, for 24 interval between doses, right? So every day the dog receives 1 dose of 0.25 mg per kg for 2 weeks. That's my first option. Now my second option is going to be, I want to now test 0.25 mg per kg, but not once a day, but twice a day. So I'm going to give 28 doses this time, right? And then we have 12 hours between doses, because it's twice a day. And we still use the dose of 0.25 mg per kg here. This is my second simulation. My third schedule this time will be, I want to test for, let's do this, for 0.5 mg per kg twice a day, right? So we've been from 0.25 mg per kg once a day, 0.25 twice a day to 0.5 twice a day. So again for 2 weeks, so 28 doses. Okay, now I've got my 3 doses I want to evaluate. I just click on the run comparison. That's fine, because you actually have, so we're going to simulate 500 dogs 1,000 times, so you have a lot of computational power behind the scene to be able to run those simulations. So that requires quite a bit of a bandwidth to be able to do that. And so when we are all in the same room with just, one of a hotel network, doesn't work that well. So let's try to launch it again. All right. So when you do have access to internet, this is what the simulations look like. So you're going to get panels with simulated PK information and simulated PD, so efficacy data, for all of the angiotensins based on the profile you have been simulating. Now, it's actually something which is nice to see visually, but you also have a tool to quantify the actual effect. And the way we do this is we calculate the area under the curve for all of these simulations. So let's say that for angiotensin 2, you're going to see a decrease of Ang2. You can quantify the area under the curve of that profile and say, okay, I've got X% reduction versus placebo for a dose of 0.5 mg per kg twice a day. So we have a way to make it easier for you guys with a tabulation of results, a summary table that tells you the percent decrease or increase of each biomarker versus placebo. And then you can just rank the various dosage and see what provides the best efficacy for those dogs in those biomarkers. So when you do this exercise, what you actually see is that the best doses that produce the most reduction of angiotensin 2 is in fact the 0.5 mg per kg twice a day. On average, you get a 50% added benefit of a 0.25 mg per kg once a day. So you do see a significant increase of efficacy by going from 0.25 mg per kg once a day to 0.5 mg per kg twice a day. And this is consistent with what we also see with angiotensin 1.7, which this time is the positive arm of the rise, right? It's the light side of the force. When you do those simulations, you have also a 50% increased benefit of this dose versus the conventional 0.25 mg per kg once a day. So those simulations actually match the information we get from specialists, from you guys, right? So we know that the tool is able to confirm your clinical judgment, so which is actually very, very positive. Now, interestingly, when you run the 0.25 mg per kg twice a day, you don't get that much difference versus the 0.5 mg per kg twice a day. You just get a 10 to 15% difference between the 0.25 mg per kg twice a day and the 0.5 mg per kg twice a day. So there seems to be some kind of a plateauing effect, and the actual increase of the frequency from once a day to twice a day does a better job than just elevating the dose from 0.25 to 0.5. Now, a word of caution, obviously. Those results are based on an experimental model of RAS activation. Now, the next step is to feed that model with new data coming from the clinic in dogs with congestive heart failure to really validate and confirm those simulations. Another value of mathematics. In math, when you have a model, you can actually make it a never-ending tool. You can feed it with new data and make it more predictive, right? In stats, you have what you have with your sample. In math, you can get more information, more data to make it more predictive over time. And so the next step in that whole exercise is to do a prospective study, hopefully early next year, involving 24 centers in the US and in Europe, hopefully a few from Spain as well, where we're going to basically run different arms of dosage of Cadalis and benazepril and see whether what we see with those simulators is actually matching the clinical response you get from those dogs. And that will be the best way to fully validate what we've been expecting with the simulator. So if you want to know more about our work, we've published this recently in Nature Scientific Reports, and so you have all of the information on the model, you have links to the simulator, so you have everything you need from that paper, and it's open access as well, so easy to access. Last but not least, obviously, I'm the one showing up today, but this is really more the work of my postdoc, Ben, who's been working thousands of hours to develop this tool in the lab. And he now moved to industry, so I'll let you decide whether he joined the light side or the dark side of the force. But we're still in touch, obviously. And at last, I want to say something which is actually extremely important, is that all of this would not have been possible without one person in that room, and this is Emily. She's been really, really supporting those efforts since 4 years now. When we met at ACVIM in 2019, she was like, well, we have an issue with the dose of benaziril, we think. I said, yep, I think I know what you're talking about. And she knew that doing this would potentially lead to a change in the label dose. And I thought, well, you know that there is a risk for the company, right? She said, yeah, but we have to do it. I said, oh, that's a first. So kudos to you, Emily, to take on that gamble and supporting those efforts since the very beginning. It's been a pleasure to present that work today to you guys, and happy to answer any question.